Okay, so I hope you can tell my lowercase thetas and phi's from my uppercase thetas and phi's, but I want to show you something. In this book, I told you there's an entire chapter dedicated to the hydrogen atom, which is here, and I should probably just take a picture of this and post it. We don't really need to read the text. But all of the math we just did to set up this problem, editing Angela, put out the timestamp of how long I've been working on this, and I want to tell you that we've just reached this equation here. He did all of what I just did in like a paragraph of text. So now what we're going to do is we're going to simplify this by multiplying everything by little r squared, and then moving all the r stuff onto one side and all the angular thetas and phi's to the other side. Alright, so we have stuff that needs r and stuff that needs theta and phi over here. And here we can use a math trick, because on the left we have a function that depends on r, and it is equal to something that doesn't depend on r. And that means that our left side has to be equal to some constant, which has to be equal to our right side. And it has to be the same constant. So we can use that to start whittling down what we don't know here. So I'm going to start with the right side, the angular part, and set that equal to c.
So we have c equals f squared over 2 mu times 1 over sine theta, 1 over theta, d theta, sine theta, d theta, d theta, plus 1 on sine squared theta, 1 over d, d squared d, d theta.
So now I'm going to do a similar trick to what I did before. I'm going to multiply both sides by sine squared theta, and then move the theta to one side and the d on the other. We're separating out our variables. So what does that give me?
2 mu over h bar squared, sine squared theta, c, minus sine theta, 1 on theta, d d theta, sine theta, theta d theta, equal to 1 on d d t.
Okay. So there's this math trick you can do where on the left we have something that depends on theta, and on the right it doesn't depend on theta. So the left side, which I'm going to call left side number 2, has to be equal to some constant, which has to be equal to the right side number 2. So the same exact trick. Very cool. Okay, let's start on right side number 2.
So we have this differential equation 1 on d squared c squared
is equal to some constant. For historical reasons, we're going to call this constant minus m squared. Now we have a differential equation that has two solutions. When m is not equal to 0, the solution to this is going to be e to the plus or minus I n phi. When m is greater than 0, the solution is going to be 1 or phi. And when you see people doing quantum mechanics and talking about m's and l's and m's and angular momentum, m is the magnetic quantum number, and it can be positive or negative. Because we're working in 3 dimensions, we have r, theta, and phi. We're going to have 3 of these quantum numbers that come out. M is the first one. Great. So we can work backwards and start working on the left side of this equation, which I have called left number 2. So we can just plug in our solution for c into our equation and start working through left number 2.
We get 1 on sine theta, d d theta, sine theta, theta d theta, equals c plus m squared on sine squared theta, theta.
And things here are just going to get really tedious. I mentioned I wasn't going to do this whole thing just because it doesn't need to be done. The thing that is going to happen after lots and lots of algebra is that c has to be equal to negative L times L plus 1. quantum number. It's the angular momentum quantum number. So you have your magnetic quantum number M, and you have L, your angular momentum quantum number. And these are important, but not for our purposes because we're looking for the Bohr radius. So I'm not going to do this method. I'm sorry. It would be in a textbook if you wanted to look it up. And that's kind of the thing too. I showed you how much Shankar is skipping in chapter 4. That's because it's chapter 4. This was a quantum mechanics course, and I had given 8 weeks of 45-minute, 3 times a week lectures. I wouldn't even need to do this algebra. You would already know where this was going, and you would just be like, oh, it's L times L plus 1. But this is a very short video, and I'm going to skip it. You're just going to have to be fine with it to deal with it. Like and subscribe. So now we have our second quantum number, and we're going to need a third one, but remember we're trying to find the wave function, the solution to the ground state hydrogen atom. So we need to take this solution and plug it back in to the angular part of our wave function solution. So we can now go back to the angular momentum part of our wave function and plug in our L's and N's, and here's where we're at.
I'm gonna write it like that. 1 over sine theta, d theta, sine theta, d theta, d theta equals minus L times L plus 1 plus n squared over sine squared theta.
The solution to this is Legendre polynomial. And again, if we were 8 weeks into a class, you would have already taken a mathematical methods and physics course. And when I said Legendre polynomials, you would be like, of course. Right? But that's okay. We're going to skip this part too. I'm just going to write down the answer. So, the Legendre, I'll write it down if you want to. Legendre polynomial looks like this. And cosine theta. Okay. And, this is enough for our purposes. We've already got our M's and our L's. We see that those are quantum numbers in addition to the one we're going to get from the R part of this equation. So now I'm just going to throw in some spherical harmonics to match my Legendre polynomials and give you the YLM part of our hydrogen atom wave function, which will look like this. Okay, so this is the answer to the angular part of the wave function. So we're looking for the wave function that's NLM, which would now look like this, psi of n. I'm just calling it that, it's fine, times y, lm of theta, and phi. Yeah, let's make that our just to be nice. I just want to remind you what we're doing here, which is finding the wave function for the hydrogen atom, which is the simplest possible atom. This is so complicated. Imagine if you were just slapping electrons all over this. No. This is very simple and nice and easy. But also remember that Bohr didn't know about any of this. When Bohr was analyzing the atom, he had one quantum number. He had n, which we're going to get to. L and M didn't exist for him yet. And I think that's really interesting. You have your little cartoon picture of your atom with your shells, but what the L and M's do to your atom look like this. Like, it's so much more complicated than nice little shells. But we're so close to finishing, so we're gonna keep going. Okay, what we're gonna do is go back to left 1. Let me remind you what it looks like. So we just did this whole bit and got this part of our wave function. We're now going to look at this little bit. I called it left 1. Okay. Let me rewrite it down.
Okay.
So we'll do another mathematical trick where to analyze this, we can look at the large R limit. So what happens as R goes to infinity? This will reduce down to everything that doesn't have an R in the bottom, and you get this differential equation. And again, the thing about differential equations is if it's possible to answer it, you just know the answer. When the solution for r here is going to be e to the minus k r. And we're choosing the negative one because these are bound to empty states. And here a squared is equal to minus 2 mu over h bar squared times e. Okay, we can check by plugging our solution into this big equation. Except we're still in the large R limit, so this will go to here. Okay, now we're so close to the end, and I am going to leave the next part as an exercise to the reader because I don't want to do it, but also I've always wanted to say that we make it as an exercise to the reader. But from here, we can get a squared is equal to minus 2 mu over h bar squared e, and you can get a is equal to k mu e squared over h bar squared. Okay, let's look at a here. So a is equal to k, which is 1 over 4 pi epsilon naught. And then there's mu. Let me remind you that mu is equal to me times mp over me plus mp. Now me is so small compared to the mass of the proton that this just ends up being me times mp over mp. And you can call that 1 and say that mu is almost nearly identical to the mass of the electron. So we can write me, and then you have e squared, and this is all over h bar squared. So h bar is equal to h squared over 2 pi, so that's 4 pi squared. So let's cancel things. You get a is equal to pi times the mass of the electron times e squared over epsilon naught h squared, and this is equal to 1 over a naught, which is the inverse of the Bohr radius. So we have now done the Schrodinger equation and landed back at the Bohr radius. I told you this would happen. Let's look at this a squared is equal to the energy thing. So a squared is equal to minus 2 mu, but remember that's just the mass of the electron, over h bar squared, which is going to be h squared times 4 pi squared times e. So now we can take what we just found for a and square it and plug it in here, and we solve for e, which gives us negative me times e to the 4th over 8 e naught h squared. And again, these are all constants or like measurable values. You can plug those in and you get negative 13.6 eV. So we've solved the ground states of the hydrogen atom, and we found that the energy is negative 13.6 eV, just like Bohr thought. So what we're neglecting here is the n squared. That's because we took this lower lower limit. That's only applying to the symmetric condition. We could go back and pull out that n, our third quantum number, if we needed to, but we don't, because we're doing it now. So what does this wave function actually end up looking like? So you usually write that as NLM, where you list your quantum numbers for the ground state. N is 1, L is 0, and M is 0. So we get psi 1, 0, 0 is equal to 1 over 8 pi a naught to 3 halves e to the minus r over a naught. And this is our wave function of the ground state of the hydrogen atom. We fucking did it, y'all. So if you were to go back and put in your n and solve with the standard wave function that works for any L and M, this is what that would look like, just for completion on this little video. is what defines what the radial probability density of your electron looks like. This is how you define the radius of not just the hydrogen atom at the ground state, but all of them. And just for comparison, remember that Bohr's was just looking at energy as a function of n. But you can't do that. It gets much more complicated. And I do want to remind you that this does get more complicated, right? This is the hydrogen atom. There's no neutrons. There's one proton. You don't have multiple electrons interacting with each other. This is the simplest case of the Schrodinger equation applied to an atom. And it's so very, very complicated. I just want to mention some quantum rules for our quantum numbers that must be obeyed because of the way our wave function is set up. So the first rule is that n, l, and m are integers, so they're counting numbers. The second is that n has to be greater than 6. You can't have an energy level that's inside your nucleus. The third rule is that L can range from 0 to n minus 1. You can't have an L that's bigger than n. And the fourth rule is that for n, it can range from minus L plus L. And let me show that picture again of what these end up looking like. This is how you get your S and P d orbitals in chemistry. We're predicted the spherically symmetric atom, and that's just not what it is. Quantum mechanics is so important. Need your L's and your N's. Right? The Schrodinger equation, which treats an electron like the wave that it is, arrives at the same value for energy that Bohr did. And that's very exciting and nice. And of course it does, because we saw it in the spectra. It has to be the same. However, the Schrodinger equation accounts for these angular momentums, your L's and your M's, that definitely exist and definitely have effect on the shape, structure, and behavior of the electron shells. Bohr does none of that. Bohr is not aware of any of that. And those L and M's, and you have even more, like you have the spin that I didn't even talk about. You have like a lamb shift, like if you slap a field on it, you get xenon splitting in the spectra. It's a whole lot of things that appear, but the radius of the hydrogen atom, which is what this video was addressing, it got the same answer, because those things, they affect the spectrum, they affect where the electron sits, and like some like really advanced level topic, it would affect the radius a little bit. But for our purposes here, Bohr and the Schrodinger equation give the same answer for what is the radius of hydrogen, and that's really cool and interesting. Of course, Bohr misses all of these other transition regions where you're moving between angular momentum spaces. He misses all these degeneracy levels. To him, all of these would look the same because he's just looking at n, but we're in the future, and we know about L and M, and we know that those levels, even though they appear to have the same energy level, are different states of the atom, and they would appear differently in the actual atom. Bohr got the right answer, but he was wrong in his approach, because in order to accurately describe the hydrogen atom, we need quantum mechanics, and we've done it. Yay! So what is the radius of the hydrogen atom? Bohr imagined an electron that's a particle orbiting your nucleus, and in that case the radius would have been just the distance from the proton to the electron. But we know now that the electron is not a particle, it's a wave, and we have a wave function that will describe the probability density of where our electron actually is. So if we want to calculate the radius, we have to do like statistics. What is the most probable state of the electron, which will give us the most probable position of the electron, which will give us the most probable radius. Angela in real time is doing the Schrodinger equation later, and I have a feeling that Angela later is going to skip the part at the end where you actually get to the wave function. So the ground state of the hydrogen atom, your psi NLM, psi 100, looks like this. Should I just put up some more just for fun? But we're looking at the ground state. So to get the radial probability density of the ground state of the hydrogen atom, we need to take the square of that wave function and multiply it by a spherical shell element, which will look like this. we can take that, drop the constants, take the derivative, and set it equal to 0 for maximum probability, and we get this, which just gives us 1 is equal to r over a naught, which we can solve for a naught and find that the position of maximum probability for the position of the electron is r equals a naught. The most probable radius of a ground state hydrogen atom is exactly a naught. 0.53 times 10 to the minus 10 meters. 0.53 angstrom. We did it again. Yay. But quantum mechanics isn't that simple. That's the most likely value. But what is the average value? What does the average hydrogen atom look like? To do that, we need to take the expectation value of the ground state wave function of the hydrogen atom. So our interval looks like this, and I'm going to be real with you. I just put this in my calculator because I didn't want to do integration by parts. I didn't solve this integral, and it gives us this answer. Evaluated from 0 to infinity for r. So everything within r in it kind of cancels, and we get that the expectation value of the radius of the ground state of the hydrogen atom is equal to 3/2 a naught. So like more than a naught. The average radius of the ground state of the hydrogen atom is like 0.75 angstroms compared to the most likely radius of the ground state of the hydrogen atom, which is 0.5 angstroms. And that makes sense because there's like a tail on this value. It can be a little bit bigger, so it's going to pull the average away from the most likely. So the average ground state of the hydrogen atom has a radius of 3/2 a naught rather than a naught. So that is the radius of the hydrogen atom, depending on how you ask the question. How you ask the question starts becoming really, really important in quantum mechanics, actually. I mentioned that in the Shankar books, he kind of takes a couple paragraphs to go into how you would actually measure this. So I thought that would be fun to do too. But like, I really care about your all's safety, and I do want to warn you in real life about something I learned from the comments of my previous video, which is that as soon as you touch a piece of lab equipment, you are no longer a physicist. As soon as you touch anything in the lab, now you're an engineer. So while we did all of the physics and all of that was like theoretical physics and very important, and wow, that's physics, we're kind of entering into engineering territory because we're going to look at the spectra of the hydrogen atom, which is apparently engineering. So be careful. I work as a theoretical physicist, but when I was in graduate school, I did a lab tour and I touched a function generator, and now I'm not allowed to call myself a physicist anymore. So I just wanted to warn you. Like, be careful out there, okay?
In your opinion, what would you expect that's going to happen in the development of physics education?
So it's a very likely field. I don't think we're going to run out of questions in the near future.
Excellent.
The thing you can measure in a lab is photon.
So the act of observation, which is pretty innocuous for you and me, right now, I'm getting slammed by billions of photons. I'm taking it like a man. But for the electron, it is not that simple. One collision with the photon is like getting hit by a truck.
The thing you can measure in a lab is photon. You measure electrons, not photons. So to look at the radius of the hydrogen atom, what you would actually do is take a hydrogen gas lamp and you would excite the hydrogen in it, pushing those electrons up to the higher energy levels, and then they would immediately come back down and release a bunch of photons, which you could observe with a piece of equipment called a spectrometer. So I just thought it would be kind of interesting to like price this out. Like, if you actually wanted to do this at home and confirm quantum mechanics, here's how you would do it. So these are called arc discharge lamps, and what they do is just like a high voltage, and you stick a gas tube in, and it will excite all the gas in that tube, causing the electrons in those atoms to go to their higher energy shells, and then they'll immediately want to go back down, so they'll go back down and discharge photons, which you can see. And I do not recommend any of these websites. I just found the products on the internet, so don't buy this. But I just thought it would be interesting to price it out. So I found one of these for like $215, and this looks exactly like the one. If you've done this experiment, we usually do it in the E&M course, like Physics 202 or 212 or whatever it is at your university. This is like the last lab you do, where you're given a random lamp and you have to identify the gas based on the spectra. This is exactly what it looked like when I did this lab. And then you would buy a hydrogen 2B. So we're at like $250. So this will be the source for your experiment. To look at the spectra, you need a device that can look at the photons that are coming out of this and plot their wavelength on a little plot for you. So you need a spectrograph. So what you want is an Ocean Optics spectrograph. That's a good brand, but they're very expensive, and I don't think you can just like directly buy them from their website. But I found them on AliExpress, and that seems like a bad decision. I think new these would cost you like $2,000 or $3,000, but I see them on used sites for like $900. I'm going to show you what the inside of a spectrograph looks like so that you can see how this experiment would work. So you can see my mouse. Okay. So here you would attach like an optical fiber, and you would stick that optical fiber right next to your source, your gas lamp that's spitting out photons. And those photons would go through the optical fiber and into your spectrograph. Okay. So it would go here, it would bounce off. I'm sure this is a mirror, and this is a diffraction grating. So what it's going to do is it's going to take the light that is coming in from your source and spread it apart. That's why this turns into a little rainbow. It's going to spread it apart so the wavelengths are separate and discrete, and you can observe them better in your detector. Then it's going to go to another mirror, and it's going to bounce all the way across to this is your detector. And this works exactly the way like it's not a CCD camera. I always jump to CCDs, but they're not CCDs anymore. It's CMOS. But what's going to happen is it's like a little silicon detector. Your photon will hit it, and this detector will receive like half of them and convert those into electrons. And the electrons will go to, the fancy thing about these is that it will go directly into a very nice little computer program. Like this thing, you will be able to attach a USB directly to your laptop, and a software will pop up and make a plot for you. So you don't even have to do that part. No math for you. You just stick it in your computer and it's like, here's the spectra. These are usually optical detectors. So you're not going to see the Lyman series, you'll see the Bumblr series. Anyway, you'll see something like this. You will see a floor and then these peaks that are going to match those discrete energy changes in your hydrogen atom. And using this spectra, you can uniquely determine what atom was in your gas. And this is how you confirm quantum mechanics. And you can do it in your own home for $1,000 to $4,000. If you want, you could buy the hydrogen lamp and then get a handheld spectrometer, which is how they used to do it in the old days. But I mean, then you have to make your own plot. So I'd really recommend the spectrograph if you're going in on doing this experiment for yourself. So that's how they would do it. And this is the kind of thing that AMO physicists are doing all the time. Obviously not with hydrogen, but like very specific atomic systems. And they can put a magnetic field through and like split the degenerate levels and do all these really interesting, very specific things that are predicted mathematically and then appear, because quantum mechanics is so good at predictions, and it's just really cool. Isn't Isn't it weird that Bohr got the right answer though? Not really. So Bohr suggests this correspondence principle where theories should kind of join, where they stop working, if that makes sense. Like, as Newtonian mechanics approaches relativity, the answers are not as correct, right? But there's this overlap where relativity and Newtonian mechanics give the same answer. And the same thing happens with classical mechanics and quantum mechanics. So Bohr was wrong, but it makes sense that he got the right answer.
Look, that's the beauty. Once you got the right answer, everything is going to be on your side.
I'd like to show that again by looking at the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle says that there's a limit to how precisely you can know a piece of quantum mechanical information. So accuracy in momentum times accuracy in position is equal to some constant. And the same thing for energy and time. These two pieces of information cannot be fully realized in quantum mechanics. So let's look at Bohr's atom again. He found that the energy of the electron in the ground state is 13.6. So that's how much energy you have to add in to kick that electron out of the atom. This is equal to 2.18 times 10 to the minus 18 joules. And we know that kinetic energy is 1/2 mv squared. So if we take that, using our known value of the electron mass, we can solve for the velocity, which gives us 2.19 times 10 to the 6 meters per second. So this is the minimum velocity of the electron in the first ground state of the hydrogen atom. And we can use that to find the minimum momentum, which would be that velocity, times the mass of the electron, which gives us 1.99 times 10 to the minus 24 kilogram meters per second. So if we plug that into the Heisenberg uncertainty principle and solve for delta x, which gives us about 0.5 times 10 to the minus 10 meters, which is, A naught, it's the Bohr radius. Even though Bohr didn't know quantum mechanics, the world still knew quantum mechanics. Even if we didn't understand that electrons are waves, they're still behaving like waves. It does make sense that Bohr could get the right answer because he's using observed values and the world follows quantum mechanics, even though he didn't know he was using quantum mechanics values. It's really interesting, but it's not that crazy. But we also know that Bohr was wrong. As soon as you start looking at anything else outside of his very nice energy levels, you can tell he's wrong. Let's look at the Heisenberg uncertainty principle again. So imagine you're looking at the n equals 2 state of hydrogen. So the electron is moved up in a higher energy level. This is not stable. The electron will almost immediately, in about 10 to the minus 8 seconds, emit a photon and go back down to the ground state. That photon is a Lyman alpha photon and will be emitted at 10.2 eV, and Bohr could have calculated that if he wanted. This behavior would have been known by Bohr. He would have expected this to happen. But because of quantum mechanics, there's an observable effect of this that Bohr wouldn't have any idea about because he didn't know quantum mechanics yet. I'm sure he learned it later in life. That's fine. I don't need to be shitting on Bohr. Like, he's wrong about everything all the time. He went through a phase of saying we should throw out conservation of energy. It's crazy. But has anyone ever been so wrong, but also so inspiring to the people around him? Like, he was wrong in a way that made other people figure out the correct answer, which is not the worst way to be. He still contributed quite a bit. Anyway, but he was wrong here. He didn't know what was about to happen. So if we look at the Heisenberg uncertainty principle again, with that situation where n equals 2 hydrogen goes down to an n equals 1. We know that delta T is 10 to the minus 8 seconds, so we can calculate delta E here, which is 1.05 times 10 to the minus 19 ergs. Who uses ergs? I hate that I've done that to you. Using the Einstein-Planck formula, we can figure out from the energy, the wavelength of light that would be, and it's E equals hc over lambda. So we get delta lambda is equal to lambda squared over 2 pi times delta Tc, which gives us 0.014 times 10 to the minus 13 meters. So that is the uncertainty in lambda. That means there's uncertainty in our ability to observe this transition on the order of 0.014 times 10 to the minus 13 meters. That means that when you look at the spectra, you don't get a nice delta function at exactly the wavelength that Bohr predicts it will be. You get a broad spectrum because we are unable to accurately observe this because quantum mechanics is real and the Heisenberg uncertainty principle is real, and we cannot exactly observe that wavelength. It's a little bit spread. It's a little bit uncertain. Bohr predicted about where the spectral lines would be, but quantum mechanics explains why are some of these lines brighter than others? Why does turning on a magnetic field shift some of these lines? Why are some of these peaks more broad than others? That's amazing. Quantum mechanics is pretty cool. How many times have I said that in this video? Quantum mechanics is cool and fun, and I recommend it. And if you're planning on learning it, this is a good textbook. I should learn how to do Amazon affiliate links or something.
I think, yeah, we all learn things which are not in our field, right? I learn about the cell, the embryo, because in some sense it affects my life. So physics will affect your life, so be aware of it. And even if you don't become a physicist, when you do physics, you learn a few things which are important. You learn how to make responsible predictions. When you say you have a theory, doesn't mean you woke up and dreamt of something. Theory is a very responsible way to speculate what will happen. It's got consequences. It can be tested. If you cannot test it, it's not a theory. And if you test it and it doesn't work, you have to be ready to give it up. And if it works, even your opponents have to accept that you're right. So these are aspects of scientific thinking that many people do not know. They say, well, I talked to this physicist, he believes that, the other physicist says, no, the opposite is true. Maybe nobody knows what's going on. That's not true. In any living subject, there will be periods when it's not clear who's right. It's not because anybody is lying, because it takes a while to figure out who's right. And if you're in a subject where you can actually establish who's right to everybody's satisfaction, that's not like many other things in life. Many other things, some people would say is good, some people would say it's bad. They can argue, they would say, let's agree to disagree. In physics, you cannot agree to disagree. There's only one answer, one choice. And in the end, everybody has to agree. That's what I like.
Yeah, don't watch me do this. This is suffering for everyone. All right. 3, 2, 1. So I was at a physics conference in November, and for some reason, me and this group of strangers were talking about Lord of the Rings. I mentioned my day when I want to watch the Lord of the Rings movie, which I do at least once a year. You know, you wake up with coffee in the Fellowship, and you have your bag of peanut butter M&Ms. By the 2 towers, there's a little bit where you can take a 13-minute nap. I'm sorry, I just don't like battle scenes. They're so boring. And then you wrap up, you cry during Return of the King, and then there's that part at the end of Return of the King where it ends 15 times, and it's kind of boring. And this guy says to me, right to my face, he says, yeah, but they left out the best part. And I think he's going to say Bombadil, which is a red flag to have a conversation with a stranger with someone who's into Bombadil. But he says to me, they left out the Scourge of the Shire. And I say, the what? So usually I talk about science and data and stuff, but today it's just Lord of the Rings. If you're not okay with that, that is okay. I will see you next time. Or you can check out my Patreon. Am I making an ad for my own Patreon? I have some science on there. But if you're new here and you're into me talking about Lord of the